think about this type of function. Let's pick a function from, let's say, from 0, 1 to the real line. And let's look at this type of function. Let's not include 0 for convenience. So think about that. Let's say that, and let's call this omega. This is now our space omega. So let's define y using this formula. Y omega is equal to 1, 2, or 3. It's 1 if omega is between 0 and 1/3. Let's make it 2 if it's between 1/3 and 2/3. Let's make it 3 otherwise. If you want to draw it, of course, it's 1, 2, 3. So it's growing 1, 2, 3 in this way from 0 to 1. Okay, this is our function y. This is our space omega. And now for this function, we could ask, what's the smallest sigma algebra that y is generating? So now we have a concrete function. So what is, in this setting, what is sigma y? It is going to be a sigma algebra on the set 0, 1, which we are denoting omega. But what is it? If we do a bit of a mental exercise, so we could play around. So we could think, okay, we know that this should contain all the pre-images of all the Borel sets on the real line. So think about the Borel set, which contains only the point 1. And then we could look, what's the pre-image of a set on the real line, which only contains the number 1? If we look, maybe another picture is good to have. So let me draw omega in this form. So this is 0, 1/3, 2/3, 1, and then this is the real line, having here 1, 2, and 3. And then we know that y maps these members there, these members to the number 2, and these members to the number 3. Yeah. So the pre-image of 1 is then the set of numbers between 0 and 1/3, including 1/3. So we find that this is, let's call it A1. So yeah, this is A1. And it's the numbers bigger than 0, less than or equal 1/3. And the same way, the pre-image of 2 is, of course, from 1/3 to 2/3, and the pre-image of 3 in the same way. Let's call it A3, and it's 2/3 up to 1. So now we know that sigma y contains A1, A2, A3, yeah, because it must contain all the pre-images. What else does it contain? Well, because this is a sigma algebra, it contains the empty set and it contains the full set. So it contains omega. So now we have these sets. Does it contain something else? What about the pre-image of the set 1 and 2, for example? What is the pre-image of the set containing 1 and 2? Well, that's of course the set which contains all these points and these points here. So it is, this is A1 union A2. And that set is also there. So we can write, and the set union A1, A2. And what else? Well, union A1, A3, of course, and then union A2, A3, this type of unions it should contain. What else does it contain? What about the pre-image of the set let's say if the number is pi from e to the pi, let's not do e to the pi. Let's do e to the pi, for example. What's the preimage of this set? Well, pi is bigger than 3, so we are looking at an interval there. There's nothing where y could map, so then the preimage of this is empty. So an empty is already there. So we are actually looking at this type of collection. We have 8 sets, empty, omega, 1, 2, 3, and then combinations of 1, 2, 1, 3, and 2, 3. Yeah. This is actually the sigma algebra. So as an exercise or as an homework, you could check that the sigma algebra generated by Y is the collection which contains the empty A1, A2, A3, the unions of these A1, A2, A1, A3, and A2, A3, and then the full union A1, A2, A3, and that's it. And we note that's union, and we know that this is this full union is the full set omega. It has 8 members, and these 3 sets here are sometimes called the atoms of the sigma algebra, because we can represent everything as the unions of these. And that's the way how to look one concrete example of the setting. Do you have questions about this example? One point, I didn't prove yet that there's no more, but that would be homework. No more. That's your homework. No más. In my opinion, we could have a break now. Yeah, this would be a good place for a break. Do you want to ask something?
A question on the preimage of the Borel set.
Yeah.
So we proved it for the Borel set, but from the proof it seems that this of course works for any sigma algebra.
Yes.
Yep.
Excellent question. Yeah. Let me emphasize this. So let me emphasize this. So imagine another setting. We have an omega, and we have some S prime here and calligraphic S prime here. And assume that this is a sigma algebra on S prime. Assume that, let's say, F is a function from omega, or actually let's put there S. Let's say this is just S. Let's now use a different symbol. So we have a function F from a set S to a set S prime. Okay. And then we say that, okay, if we define sigma of F as the smallest sigma algebra containing the collection of all pre-images in this sigma algebra. So that would be a way, instead of now real line and the Borel sets, we would have any set and any sigma algebra. This would make sense. And we could ask, okay, what about the proof that we did, that we showed? Previously, we showed that for the real line and Borel sets, what happens is that this is already a sigma algebra. So there's no need for this sigma, and we could just delete this and say that this is all the pre-images of S calligraphic prime. Now, I think your question is, was there something in the proof that we kind of used the properties of the real line? Or does this work for every sigma algebra? And
it seemed quite straightforward that it works.
Yes, it is rather clear. There was nowhere, I was not hiding any property of the real line. I was not trying to fool you that, okay, there was something crucial about the real numbers that we used kind of hidden inside the proof. No, that didn't happen. this was an honest proof that and that proof really works for any sigma algebra as you suggest and as you very well pointed out. So yes, we can say this is okay in really general setting. I was just using the Borel sets to kind of maybe help you to be on the map a bit, that okay, there's something related to numbers as well in this game that we play. Maybe one more question before we retire for a break. Maybe one point to close is that in case we have some sigma algebra F here, the way to look at this is that you could think that there's omega, and there's kind of a grid which is representing the F. So in some sense, you could think of the sigma algebra F as being kind of a grid here in the space. Okay, it would be an infinite grid in general, so it would be kind of it would have a kind of infinite precision up to, yeah. But anyway, and then you could think that there's some function y from to the real line, and you could ask, okay, what are the pre-images of there? So they might be kind of coarser sets here. And then in that sense, the sigma y would be kind of a coarser grid. So you could think that, okay, y is kind of also creating a grid here, but is somehow more coarse. And the pre-image of y are kind of bigger sets here of this type of form, whereas the atoms of the original sigma algebra would be something finer. So this would be kind of fine collection, and this would be kind of we know that this sigma, if y is now, we assume that it's a random variable. So then we have here, we have this space F, which is fine. And this is what we are calling coarse as kind of a grid. All of this actually, what you have learned now, kind of secretly, you have also learned something about topology. Topologies work the same way. In case you once learned about abstract topology, so there are fine topologies and coarse topologies, and they kind of work precisely the same way.